Hello everyone, and welcome to this session where we explore a fascinating problem in electromagnetism. We're going to determine the electromagnetic energy density and the total energy stored within a cubical box containing uniform electric and magnetic fields. This problem is crucial for understanding how energy is stored and transported in fields, a foundational concept in physics. First, let's visualize our setup. Imagine a simple cubical box. Within this box, we have a magnetic field, let's call it B, that is uniform, meaning it has the same strength and direction everywhere inside. We also have an electric field, E, which is also uniform throughout the box. Now, let's identify our key variables and constants. The magnetic field strength, B, is given as 0.02 Tesla. The electric field strength, E, is 2.5 times 10 to the power of 6 newtons per coulomb. The edge length of our cubical box, L, is 12 centimeters, which will convert to 0.12 meters for our calculations. We'll also need two fundamental constants: the permittivity of free space, epsilon naught, which is approximately 8.85 times 10 to the power of minus 12 farads per meter, and the permeability of free space, mu naught, which is 4 pi times 10 to the power of minus 7 henries per meter. Next, the relevant equations. The energy density stored in an electric field, which we'll call UE, is given by 1/2 times epsilon naught times E squared. This tells us how much energy is packed into each unit volume due to the electric field. Similarly, the energy density stored in a magnetic field, UE, is given by B squared divided by 2 times mu naught. This is the energy per unit volume due to the magnetic field. A total electromagnetic energy density, U, is simply the sum of these two, UE plus UB. Once we have the energy density, the total energy U stored in our box is found by multiplying the total energy density by the volume of the box. For a cube, the volume V is L cubed. Let's plug in the numbers and calculate. For the electric field energy density, UE equals 0.5 multiplied by 8.85 times 10 to the power of minus 12 farads per meter, multiplied by 2.5 times 10 to the power of 6 newtons per coulomb squared. This calculation gives us UE approximately equal to 27.656 joules per cubic meter. Now for the magnetic field energy density, UB. UB equals 0.02 Tesla squared, divided by 2 multiplied by 4 pi times 10 to the power of minus 7 henries per meter. Calculating this, we find UB is approximately 0.159 joules per cubic meter. The total electromagnetic energy density, U, is the sum of UE and UB. U equals 27.656 plus 0.159, which gives us approximately 27.815 joules per cubic meter. Finally, let's find the total energy stored in the box. First, the volume of the cube. V equals 0.12 meters cubed, which is 0.001728 cubic meters. Now the total energy, U, is U multiplied by V. U equals 27.815 joules per cubic meter, multiplied by 0.001728 cubic meters. This results in a total energy, U, of approximately 0.048 joules. Let's check our answer for consistency and accuracy. The units we obtained, joules per cubic meter for energy density and joules for total energy, are correct. It's also interesting to note that in this specific problem, the energy stored in the electric field is significantly larger than that in the magnetic field. This often happens when dealing with very strong electric fields. In conclusion, we found that the total electromagnetic energy density in this region of space is about 27.8 joules per cubic meter, and the total energy stored within our 12 centimeter cubical box is approximately 0.048 joules. This problem beautifully demonstrates that energy is not only stored in matter, but also directly within electric and magnetic fields themselves. This principle is fundamental to understanding phenomena like electromagnetic waves, where energy is transported through space by oscillating electric and magnetic fields, even in a vacuum. The concept of energy density in fields is crucial for the design of devices, like capacitors and inductors, which store energy in electric and magnetic fields, respectively. This problem reminds us that electromagnetic fields carry and transport energy, a core concept described by Maxwell's equations. Understanding these energy densities helps us comprehend how energy flows in various electromagnetic systems, from simple circuits to light propagating across the universe. Thank you for joining this session. If you found this explanation helpful, please consider giving it a like, sharing it with your friends, and subscribing to the channel for more physics and mathematics content. Feel free to leave any questions or comments below. And if you have a specific problem you'd like to see solved in a future video, you can support the channel through a donation, and each month we'll select a few problems to feature.